If I look at the next one, for this one, the first thing I want to do is come up with my domain restrictions. I set the denominator equal to 0, because that's the one thing I'm not allowed to have is a denominator that equals 0. So essentially I say this cannot equal 0. And then I solve it by factoring. I build a bridge. That's a 9, two numbers that multiply to a 9 but add to a 10, or a 9 and a 1. So this is going to factor into an x plus 9 and an x plus 1. And again, it can't equal 0, so now I say that each of these factors cannot equal 0. And I solve each. Here I subtract the 9 from each side. That gives me x cannot equal a negative 9. Here I subtract the 1 from each side. So I find out that x cannot equal a negative 1. And now I actually want to simplify this thing. To reduce a fraction, I just need to factor this thing completely. So I factor the numerator by building a bridge. That gives me a 1. The two numbers are a 1 and a 1. So this factors into an x plus 1 times an x plus 1. Or if you want to write that as an x plus 1 squared, that's fine. But I'm going to wait until after I cancel things out because it's easier to see. The denominator, I build a bridge and factor. And once again, it's going to factor into an x plus 9 and x plus 1. I already factored it once over here when I was solving. Don't go through that work again. And now I cancel out any common factors. Numerator and denominator have an x plus 1 in common, which means this reduces to an x plus 1 over x plus 9 with the restrictions that x cannot equal a negative 9 or a negative 1. And that's it. If I look at number 18, number 18 with multiplication, we're not going to worry about the restrictions. We just want to get in that habit now when I'm reducing these things. But for this one, I'm just going to do the simplification. I'm going to factor everything as far as I can. So the 4x plus 10, I can factor a 2 out of there. So that gives me a 2x plus 5. In this denominator, I build a bridge. That gives me a negative 12. And two numbers that multiply to a negative 12 but add to a negative 1 are a negative 4 and a positive 3. And I can use my shortcut on that one because, once again, I have a leading coefficient of 1. In the second numerator, I'm going to do the same thing. Leading coefficient 1, I build a bridge. Two numbers that multiply together to give me a positive 4, but add together to give me a negative 5 are a negative 1 and a negative 4. And then this denominator might take a little bit more work if I take it off to the side here. And the reason I'm taking this one off to the side and I didn't with the others is because this does not have a leading coefficient of 1. I build a bridge, I get a negative 10. The two numbers are a 5 and a negative 2. But I have to split up the middle coefficient, the middle term, and factor by grouping because I can't use that shortcut on this. So I do the 5x minus 2x minus 5. And now I do my factoring by grouping. Out of the first two terms, I can factor out an x, which leaves me with a 2x plus 5. Out of the second two terms, I have to factor something out. So I'll factor out a negative 1, which leaves me with a 2x plus 5. And now I can see my two factors. The 2x plus 5 is one of them. And when I take that away, I'm left with an x minus 1. Okay? So now I look for common factors. I can cancel out anything in a numerator with anything in a denominator. I can cross-reduce. So the 2x plus 5s are gone. The x minus 1s are gone. And even the x minus 4s disappear. So when I look across that numerator, the only thing I have left is a 2. When I look across the denominator, the only thing I have left is the x plus 3. So that's my simplified version. Okay? Number 19 is very similar with the exception of one step, and that's the first step. Okay? If I want to do division, dividing by a fraction is the same as multiplying by the reciprocal. So the very first thing I do before I get into this problem at all is I just flip that second fraction, okay, so that I can change this whole thing to multiplication. Because I don't want to divide, I want to multiply instead, so I change this to the x squared minus x minus 6 over the x squared minus 9. Now it's just like the problem before it. I'm going to simplify this by factoring everything completely. I have this numerator, I can factor out a 3, which leaves me with a 2x plus 1. This denominator, once again, I might have to take this off to the side a little bit just to work this out. I'll take it down here. So I've got 2x squared minus 3x minus 2. I build a bridge. That gives me a negative 4. The two numbers that multiply to a negative 4 but add to a negative 3 are going to be a negative 4 and a positive 1. Can't use my shortcut, so I've got to split up that middle term and do my factoring by grouping. Out of the first two, I can factor out a 2x, which leaves me with an x minus 2. Out of the second two, I have to factor something out, so I'll factor out a 1, leaves me with an x minus 2. So my two factors are the 2x plus 1 and the x minus 2. Let me try again. The x minus 2. There it is. In this second numerator, I'm going to multiply the first coefficient times the last, get a negative 6. The two numbers that I'm looking for are a negative 3 and a positive 2. And I can use my shortcut because there's a leading coefficient of 1. X squared minus 9, that is a difference of squares, factors into an x plus 3 and an x minus 3. And now I start canceling out any common factors that I might have. The 2x plus 1s cancel out. The x minus 3s cancel out. And it looks like that's about it. So that leaves me in my numerator with a 3 and an x plus 2. In the denominator, it leaves me with the x minus 2 and an x plus 3. And that's my simplified version. Okay? If I look at the next one, this time I have subtraction. Remember, with addition and subtraction, I need to get common denominators. All right? And the best way to get common denominators here is to factor this thing first. So I factor these denominators. This one factors into an x minus 4 and an x plus 2. The second denominator is going to factor into an x plus 5 and an x plus 2. And now I basically look and see what they have in common and what they each need. I want to make sure that each of these denominators has all of the same stuff. So right now they each have an x plus 2. The second denominator has an x plus 5 and the first one doesn't. So I'm going to give the first one an x plus 5. For the second one, now if I look at that first one, I've got an x plus 5, an x minus 4, and an x plus 2. The only thing that the second denominator doesn't have now that the first one does is the x minus 4. So I'm going to give him an x minus 4. Because that just seems fair. It seems right. And remember, this is my analogy here. This is just like raising children. You've got to make sure they all have the same stuff. You've got to play it fair. All right? In this numerator, I'm going to have to multiply this out. So I'm going to have to FOIL or distribute. That's going to give me an x squared plus 8x plus 15. The denominator I can just leave in this factored form by just writing each of these side by side. Up here, I have to distribute this guy as well. That's a 3x squared. That's going to give me a minus 12x and a plus 6x, which is a minus 6x minus 24. For, once again, the x plus 5, x minus 4x plus 2. And it doesn't matter what order you put those in. It's all the same thing. And now I can actually subtract these numerators. My recommendation is change it to adding the opposite so you don't make a sign error. But when I do that, I end up with a negative 2x squared, a plus 14x, and what looks like a plus 39. Okay? And then from there, I can see if that numerator is going to factor to see if anything's going to cancel with my denominator. But nothing is going to cancel with my denominator, so I'm just going to leave it the way it is. That's it. If I look at the next one, I want to simplify this guy. I want to leave these in radical form. So for something like the square root of 72, I want to find perfect squares that divide evenly into 72. 72 I can break down into 36 times 2. That's the largest perfect square. And even if you find a smaller one, you can take the perfect square of that and then maybe find more perfect squares. But I'm going to go right for the largest one. The square root of 36 is 6. Goes to the outside. He's a changed number on the outside, but his buddy 2 is still trapped. So it's 6 root 2. For the next one, I do the same thing. I'm looking for perfect squares. For the 12, I can break down into 4 times 3. For variables, for a variable to be a perfect square, the exponent just has to be divisible by 2. So I'm going to break that into x to the 4th times x. The y squared is already perfect because it's got an exponent that's divisible by 2. The square root of 4 is a 2. It goes to the outside. It's a changed number on the outside. The square root of x to the 4th is x to the 2nd. I divide the exponents. The square root of y to the 2nd is just y. Once again, I divide the exponents. And then under my square root, I still have a 3 and an x trapped underneath there. So there they are. Okay? If I look at the next one, this one is a cube root. So I do the same thing, except now I'm looking for perfect cubes. So perfect cubes that divide evenly into 16. 8 is a perfect cube, so 8 times 2. Now for a variable to be a perfect cube, the exponent has to be divisible by 3. So I'm going to do this as x to the 3rd times x. The y squared, really, there's no hope for. There's no way to make that 2 divisible by 3. So I'm going to leave it the way it is. It's going to be trapped in there forever. The square root of 8 is a 2. Goes to the outside. It's a changed number on the outside. The cube root of x to the 3rd is x. Changed variable on the outside. And now I've got the 2, the x, and the y squared all still trapped underneath a cube root. So 2x y squared trapped under a cube root. And then looking at the next one, I want to add these things together, but in order to add things that have radicals, I need like radical terms. It has to have the same radicand with the same root symbol. And right now this doesn't. So the first thing I want to do is try to simplify it, see if I end up with like radical terms. The 18 I can break down into a 9 times 2. The 2 I can't really do anything with, but now the square root of 9 is a 3. So I get 3 root 2 plus 3 root 2. And now I do have like radical terms, so if I have 3 root 2's and add 3 more root 2's, I end up with 6 root 2. And we kind of treat those the same way we do variables in terms of adding the coefficients and leaving that radical part the same. Okay? For the next one, I want to rewrite this using rational exponents. And just remember that a rational exponent, if I have x to the 7th, doing the 4th root of something is the same as raising it to the 1/4 power. And then I multiply the exponents, and that's a 7/4. And really, the thing we need to remember here is that the exponent becomes my numerator, the root becomes my denominator. Okay? If I apply that shortcut to the next one, again, the exponent, the 5, becomes my exponent, the numerator. The denominator becomes my root. So I'm going to write this as the square root of x to the 5th. Okay? And really, with the square root, I don't typically write the 2. So I'm just going to leave it like this. Okay? The square root of x to the 5th. That's it. For the next one, I want to multiply this out. In order to multiply these, I've got to distribute or FOIL. So I distribute the 4. That gives me an 8 minus 4 root 5. Remember, stuff on the outside times stuff on the outside, stuff on the inside times stuff on the inside. Here, when I multiply this guy through, I get a 2 root 2 and then a minus root 10 because the root 2 times the root 5, they're both on the inside. I can multiply them. And then I look for like radical terms. I don't see any. I look to see if I can simplify any of the roots. I can't. So it stays like this. Okay? The next one, I apply the same thing. I'm going to distribute the root x. Things on the inside times things on the inside. That's a root 3x minus a root 2x. And then I do the same thing with the negative root 3. So that's going to be a negative root 9 plus a root 6. And now I look to see if anything can be simplified. The square root of 9 is a 3, so I can write him as a 3. But really nothing else is like radical terms here, so I can't combine anything else. So I'm just going to leave it the way it is. Okay, that's the best I can do. All right? For these last two, I'm rationalizing the denominator. Remember, rationalizing the denominator just means eliminating all the radical terms from the denominator. For this one, when I have a single term, I just want to multiply it by itself. In the numerator, when I distribute that guy, it's going to give me a 2 root 3 plus the square root of 9. In the denominator, I get root 3 times root 3, which is the square root of 9. And then again, just simplify everything as far as you can. The square root of 9 is 3, square root of 9 is 3. And I can't reduce that fraction anymore, so that's the simplified version. That's what I want. There's no more square roots. There's no more radicals in the denominator. For number 30, I want to do the same thing, except when I have a binomial here, in order to get rid of the radical symbols, I need to multiply by the conjugate. So instead of 2 minus root 3, I do 2 plus root 3. Okay? Which means in my numerator, I'm going to have to FOIL. In the denominator, I'm also going to have to FOIL. When I do that, in the numerator, I distribute the 4. That gives me an 8 plus 4 root 3. I distribute the root 3. That gives me a plus 2 root 3 plus the square root of 9. In the denominator, that's going to give me a 4 plus 2 root 3 minus 2 root 3 minus the square root of 9. And now I just simplify things. I clean it up a little bit. I've got 8 plus 4 root 3 plus 2 root 3 plus 3, because the square root of 9 is a 3. In the denominator, these can cancel out. They're like radical terms. I add them up, I get a 0. Now down here I have 4 minus, well, the square root of 9, which is a 3. And now as I go to simplify this, look what happens. In the numerator, I can add these guys together. Those are like terms. So I get an 11 plus 4 root 3. The 4 root 3 and the 2 root 3 I can combine into a 6 root 3. And that's all over 1. So this is just 11 plus 6 root 3. And that's it. Hope this was helpful, and good luck on your test.